So today we're going to discuss line integrals. Okay, so what do we mean by line integrals? So it'd be best to kind of do a little bit of a review of the different types of integrals we've covered so far. So the first thing we covered was integrals dA. These are area. And of course, after we did dA integrals, we did dV integrals of volume, dV. And we put a capital V on there, so that's a volume integral. And here we're talking about f of x and y, and here this is a f of x, y, and z. So we're talking about some sort of region in two-dimensional space here, and here we're talking about a region in three-dimensional space. Then after we did integrals like that, we also talked about integrals d of some function ds, and this was a surface integral. So we see we're talking about two and three-dimensional objects here, whether they're surfaces embedded in three-dimensional space or they're regions of volume that we want to integrate a function over, or we have some sort of a function that's defined over some area. All right, but so now we're actually going to go down to 1D. We're going to do line integrals. So we're going down to a single dimension, but we're going to do line integrals over functions f of x comma y. All right, so we're going to take so we have here our have our xy plane, and we'll have some sort of starting point, and we make some sort of curve going through the xy plane, and we can define that x of t is x, right? And y of t is y. And we say that t runs from a to b. So here we have some point t equals a, and here t equals b. And we can think of these parametrically defined functions as producing a sort of particle movement, like a little movie of this particle moving along in two-dimensional space. All right, and then we also have some function f of x and f of y. So f then is some function that lives, we'll just kind of draw it like this, as a surface, like that. And so every point on this line then defines like that, some z-axis on top of it, like that. So, like that. Okay, hopefully I can draw that good enough. So we can define a z coordinate on top of that. So really what we're talking about is a z is that we have a z of t function that's implicitly defined here, f of x of t and y of t. Okay, so with this sort of situation, we want to then be able to write down an integral of the form of a line integral, and we're going to call it the integral, and it's going to be a single integral symbol times c, and c of course is our line here. We're going to call that our curve going through space. We'll call that c, and this defines c. And we're going to integrate f of x comma y ds, and this is a lowercase s. So we're talking here, this is a small line segment. So what do we mean by that? We mean, like any integral, we're always going to be partitioning our space or our curve up into little segments, and each one will be a delta s. And we want to know how what the function's basic value is over there. So it'll take some sort of basic value. We'll call that f of I. And then essentially what we're going to do then is we're partitioning the t space here like this into a bunch of segments, and that's going to create some sort of, it's going to be approximately some sum of I equals 1 to n of f of x of I, y of I, times delta s, and I'll put that of I as well. So these delta s's all could be different depending on their lengths and how fast one travels through this curve as a function of t. Okay, so that's the basic setup here. Again, at the end of the day, an integral is always just adding up a bunch of function values weighted by some little segment of that represents how much of the line we're covering as we go through this curve. Okay, so there we go. There's the abstract definition. But the question then is, how to compute delta s. So how do we get that? So one thing we need to do is let's draw this curve from the bird's eye view. Like, there we go. Again, that's t equals a, and that's t equals b there. And at some point, we'll say that's at a time t, and then here is a time t plus delta t later, right? So there's a starting and ending point. And we want to know, again, this segment in between there, that's a delta s. So how do we get delta s? Well, certainly the delta s can be gotten from having a small delta x. So there's the displacement in the x direction, and there's also a displacement in the y direction. All right, so then delta s is going to be achieved by doing the Pythagorean theorem, delta x squared plus delta y squared. All right, so then the question then is, how do we get delta x and delta y? Well, we know that delta x, is going to be equal to x at time t plus delta t minus x at t, right? It's the difference from here to there in just the x function. Likewise, we have delta y is x of t plus delta t minus, this would be y of t. All right, so but we know from doing a linear approximation theory, we're going to assume this curve is smooth in the sense that both x of t and y of t have derivatives. We won't talk about any curves that have jagged edges on them. We're just going to talk about smooth curves. And we can represent this difference then as a derivative. So this is approximately equal to a derivative dx dt times delta t, and that's approximately dy dt times delta t. Okay, and so we're going to evaluate these derivatives at that first time t right here. So that represents how much we go this way times a small amount of time, and the difference in y's is represented by the gain of y as a function of time times a small interval delta t. Okay, so there we go with that. So that means that delta s then can be written as x prime times delta t quantity squared plus y prime times delta t quantity squared. All right, we can factor out the common factor of delta t squared and get root x prime quantity squared plus y prime quantity squared times delta t now on the outside of the square root symbol. All right, and then of course, as usual, ds then is gotten from taking delta t to 0, and we get root x prime squared plus y prime squared dt. Okay, so there we go. So as a way to represent this abstractly then, now we have a concrete way of doing this. We can now replace ds now with something in terms of dt. So we're going to do the integral from a to b. So this again is the abstract representation of the integral, and this is the constructive way we actually compute it. Either we do it numerically, as by partitioning in terms of a bunch of little line segments, or we go f of x of t, y of t, times root x prime squared, y prime squared, dt. So that's our definition of how to do a line integral for a 2D function where the curve is in the plane, in the xy plane. So let's do one example to close this out. So let's talk about a particular path. So our c in this case will be a half circle. And we're going to go like this. So there's the origin, 0, 0. We're going to start here at t equals 0 and go to t equals pi, and the circle is going to go like this. I'm going to draw that again, better. Half circle with radius, and I'm just going to make the radius 2 just for interest. So that's t equals 0 and we're at 2, 0. And here at t equals pi we're at negative 2, 0. All right, so how do we write that down? We have to write down our parametric equation. Oh yeah, first we also have to write down what our f of x and y are. And we're going to just do a simple example here. We'll do x plus 1 times y. Okay, so this is a nice function, and this is a well-defined path. So how do we write down the parametric equations? Well, I'm going to say x is equal to, x of t is equal to, it's going to be 2 cosine t. That works out, okay? And then there's also y of t is equal to 2 sine of t, all right? And then what we have to do then is find out what's our ds. Well, it's going to be, well, to find that we need to find x of t and y of t, or x prime of t. So x prime then is going to be negative 2 sine of t, and y prime is going to be 2 cosine of t. All right, so ds then is going to be quantity squared 2, and we put x prime of t in there, so it's going to be sine t. I'll put a negative sign in there, plus 2 cosine t, quantity squared dt. That becomes a 4. We can factor that out of everything. We have a sine squared t plus cosine squared t dt, and that becomes a 2. And sine squared plus cosine squared is 1 dt, so that's going to be 2 dt. So that's our path, and we have now the way in which we'll talk about ds, and it turns out they're very nicely well defined. And now then so we write down our abstract integral c f of x and y ds, where that's a little s, and now we're going to write it down as 0 to pi. The constructive definition of this integral will be 0 to pi, and now we have to put in x and y. So x then is 2 cosine t plus 1 times sine of t times 2, that's a 2 sine t times 2 dt. Oops, sorry, I'm running out of a little space there. All right, so we can bring that over here and compute this out. What we can do is we'll do a little, actually we'll just do a little bit of work to simplify this out a bit. So we're going to multiply in the sine to both parts, so we get a 4 cosine t sine t plus 2 sine t dt. Oh, and then we have a 2 from here that we forgot about, so we have to make that a 4 and make this a 8. Okay, good. So let's compute this. So this part, the antiderivative, is pretty straightforward to find. It's just going to be negative cosine. So I'm going to do that right off the bat here. That's going to be negative cosine t, evaluated at 0 to pi. And then this part of the integral, we need to, I'm going to kind of do the calculation over here a bit. Just do this right. So we'll say let u equal sine of t. So that will be, actually I'm going to let u be sine of t. And so du dt is going to be equal to cosine of t. So du over cosine t is equal to dt. So this integral here, so then we evaluate sine of t of 0 is 0, and then sine of pi is also 0 of, and then we get an 8 out front, and then we get a du, and this integral is from 0 to 0, and it's u. Okay, so so let's just compute this all the way through. Just to check, I mean, it should be 0, right? Because we have no interval of which we're integrating over, so it becomes 8u squared over 2 evaluated at 0 to 0, and that becomes 0. All right, so that part of the integral goes away. We don't need to think about it anymore. All we're left with is here. So we have 4 1 minus a minus 1. And so that becomes a 4 times 2 is equal to 8. So there we go. That's how we compute a line integral for this particular example. Thank you very much.